Wow. This book is bowling me over. This is a lot of bowls, but, I really think bowls are going to be the next Pokemon, and only 499 to go. All right. It is afternoon on a rainy Monday here in Southern California, so it is time for our second econometrics lecture of the week. Let me go ahead and switch my microphone up. Let's see if I can get this turned around towards me a little bit. And all right, we should be all set. So the topic of today's lecture is multicollinearity. This is your second video this week. Multicollinearity and heteroscedasticity, they're not actually very similar issues, but in terms of what I think about them in this class, I think about them similarly because they are both OLS violations that we need to be concerned about, but they're also both relatively easy to fix. And so because of that, because they're both actually relatively easy to detect and relatively easy to fix, we go through them fairly quickly. So I'm hoping this is another relatively short lecture. So let me go ahead and pull open or share my screen. I guess before I'll start with our table of kind of the table of the second half of this class. And last lecture we talked about pure heteroscedasticity and impure heteroscedasticity. Today we're talking about multicollinearity. And in class so far, when we've talked about multicollinearity, there's two types, like with heteroscedasticity. There is what is called perfect and imperfect multicollinearity. And you are more than forgiven if you fail to remember, don't want to remember, perfect versus pure. If in your final project you refer to something as pure multicollinearity when it was supposed to be perfect multicollinearity, I don't care at all. But kind of understanding the distinction between the two types of multicollinearity is going to be important in the same way that it's important for heteroscedasticity. But don't sweat the pure versus perfect. It's kind of impossible to remember, and I switch them up and probably will switch them up in this lecture. So, like with heteroscedasticity, perfect multicollinearity is the multicollinearity that we've been talking about all class. When we talk about the classic OLS assumption violation, we are talking about perfect multicollinearity. And so because of that, we kind of already know the definition of perfect multicollinearity. Perfect multicollinearity is when two or more variables in your model, two or more explanatory variables, are perfectly correlated with each other. They are perfect linear functions of each other. So this could be hours of sunlight and hours of darkness. It could be budget in dollars and budget in thousands of dollars. It could be a dummy variable for being a large business, where 0 means you're a small business, and then also a dummy variable for being a small business, where 0 means you're a large business. Where if you know the value of one, you automatically exactly know the value of the other. So that's perfect multicollinearity. And the reason that we can't have perfect multicollinearity in our model, the consequence of it, is that it's impossible, if we think about hours of darkness and hours of sunlight, it's impossible to kind of think about holding one of those constant while changing the other one. In other words, it's going to be impossible for the regression to distinguish the effect of one or the other. If you're looking at the effect of hours of sunlight on maybe people's happiness, you can't distinguish whether the impact is, oh, we got 1 extra hour of sunlight and that's what we like, versus, oh, we got 1 fewer hour of darkness. The two things are mechanically the same, and so you're never going to be able to separately identify either of them. When it comes to perfect multicollinearity, I'm actually just going to go through this one, or all the way up to detection right away before I introduce imperfect. The main way to detect it is theory. It really should be the case that before you even run a regression, that you don't have perfect multicollinearity in there, because you should know your data well enough, you should know your situation well enough to be aware of if two variables are maybe exact functions of one another. That said, it does happen sometimes, and maybe it might just be a small sample issue, or it might be the kind of two variables that you thought represented different things but are actually derived from the same primary object. Imperfect multicollinearity is when two explanatory variables in your model are highly correlated. Imperfect multicollinearity, really, I'm going to delete the number 6 here, because technically it's just a violation of assumption 1 that the model is correct. When you have imperfect multicollinearity, sometimes actually nothing is even wrong. So I'll put an asterisk and say sometimes. Sometimes imperfect multicollinearity is not a violation of an OLS assumption at all. Sometimes it's okay. The reason that we're going to talk about imperfect multicollinearity, though, is that when you have really highly correlated explanatory variables, often your standard errors are going to be biased. And it can make your regression difficult to interpret. So I'm going to switch to the slides now. I'll come back, like I did last lecture, to kind of fill in the detection and correction cells on this grid towards the end of the lecture, but I just kind of wanted to introduce the topics in the context of where we've been going this semester, and now we're going to dive in to the material. Okay, so perfect multicollinearity, violation of assumption 6, and it is when two explanatory variables are perfect linear functions of each other. So again, that means that, hours of sunlight, for example, would be 24, alpha 0 in this case would be 24, alpha 1 would be -1, so 24 minus hours of daylight. If you're looking at businesses that are all in the same county, so they face the same tax rate, it might be that a company's total revenue is equal to 0 plus 0.8. Say the tax rate is, or maybe 0.08, an 8% tax rate. Total revenue, tax revenue in this case, X1 is tax revenue is equal to 0.08 times total revenue, which might be X2. There's lots of examples of this that you could come up with. Same with it might just be that being a large business, if that's your X1, is equal to 1 minus being a small business. All right, and so we've seen multicollinearity in this class before, and we know that Stata can't kind of distinguish the effects of it. So here's a couple of just mechanical examples. Distance between two cities. If you're measuring it for each city, right, the distance from LA to San Diego is one variable, and then the distance from San Diego to LA is the other variable. Percentage of people voting for something versus percentage of people voting against it. Perfect multicollinearity is pretty easy to spot in your data because the variable or the data will look like an exact line. Might be positive, might be downward sloping, but the two variables are exact functions of each other. There's no residual, in other words, when you map one against the other. We've talked about the consequences of perfect multicollinearity, which is that OLS is incapable of kind of separately identifying which one is the real effect. And because they're the same thing, really there only is one effect. Maybe a better way of stating the problem is that you're pretending that there are two separate effects when really there's only one thing happening. So imperfect multicollinearity is a little subtler and a little bit more of a gray area because you're always going to have explanatory variables in your model that are correlated. If we think about the lab that you guys just did in class when you're looking at the impact of wage as a function of someone's looks, someone's education, and someone's experience, and maybe whether or not they live in a big city, the more educated people are more likely to live in a big city. Kind of end of story. Those two variables are correlated. Higher education means higher likelihood of living in a big city. Is that imperfect multicollinearity? Well, you don't know yet. I haven't told you what our threshold is. The answer, though, is probably not. It is okay if two things are correlated with each other. We have lots of things in this world that kind of move in similar directions. The bar for imperfect multicollinearity is usually going to be two explanatory variables that you would kind of describe as virtually the same if you were talking about them in just normal parlance. Most people would not say that your education level and whether or not you live in a big city are kind of like basically the same thing. Sure, they're correlated, but that kind of mental threshold might help you with this. So a graph of imperfect multicollinearity, your data might look something like this. Really small residuals overall between two explanatory variables. When you have either type of multicollinearity, your coefficients, your beta hats, are still unbiased. So remember, this is not one of the OLS assumptions that causes bias in the beta hats. Instead, it causes bias in the standard errors. It screws with your statistical significance. So typically, the variance in your standard errors will go up, your t-scores will go down. You might be less likely than you should to kind of find statistically significant results. And the other, this is kind of just saying the same thing. When you have imperfect multicollinearity, your estimates might become extremely sensitive to small changes in the specification. And that's we're gonna see an example of that. I think it's easiest to see in an example, but when two things are super highly correlated with each other, the regression kind of has a hard time figuring out which one is the real one, maybe causing the effect or impacting the outcome. And slight changes to the sample could totally flip the direction of the sign for one or more coefficients, which we don't normally have. Also, the fit of the equation might appear too good, kind of unrealistically strong. You might be really happy with your adjusted R-squared when it's not due to a good quality model. It's due to this imperfect multicollinearity. Your regression might also become really hard to interpret, and we'll see an example of that in just a second. So, well, I guess we'll see this example, and then I'm already thinking ahead to when I do a quick example for UN's data. So let's think here where if the outcome variable was maybe consumption of a student, maybe in college or something, and we're trying to explain student consumption as a function of their annual income, their total assets, so that's going to be a combination of maybe like their savings, if they own any stocks, value of any other, maybe the value of a car that they could theoretically sell to kind of get money for it, and an error term. The idea here is there could be really high correlation between someone's disposable income and the total value of their liquid assets. People who earn more money, students who earn more money might be more likely to have kind of more in savings as well than otherwise. So this might be a situation where you suspect, at least at the start, imperfect multicollinearity between the two. We're not worried about perfect multicollinearity in this case. If I asked you, my student, your disposable income, and you told it to me, I could not with 100% accuracy tell you the value of your liquid assets. That would need to be the case for it to be perfect multicollinearity. So we're not worried about perfect here. We're thinking along the lines of imperfect multicollinearity. And to give you a sense of what it means that a regression might kind of be sensitive based on having two highly correlated variables, if we include both of these variables in the model, the impact of $1 extra in disposable income, it increases your consumption by about 50 cents, holding your liquid assets constant. However, when we take liquid assets out of the model, the coefficient on disposable income goes from 0.5 up to 97. In other words, $1 extra of disposable income means 97 cents more of your consumption. The R-squared of the models are actually pretty darn similar. So taking liquid assets out of the model doesn't impact the overall fit of the model too much. And notice that there's been something screwy with the standard errors. In the first model, both of our t-statistics are insignificant, and that should strike you as odd that knowing how much disposable income a student has is not a significant predictor of how much they consume. That kind of goes against all sorts of economic theory. Our standard errors are really high, 1 and 0.09. Once we take liquid assets out of the model, though, things return to kind of what more of a normal situation that we would expect. Everything in economic theory tells us that how much money someone earns, how much disposable income they have, should impact their consumption. And sure enough, when we remove liquid assets from the model, we get a much smaller standard error, about 10 times as small, and a highly statistically significant t-statistic. Or really, I should be technical here, a highly statistically significant coefficient that we know is statistically significant based on the large magnitude of the t-statistic. T-statistics themselves are not significant, the coefficients are significant. All right, so how can you tell if you have multicollinearity in your model or not? because it exists to some extent in every equation. If it's just defined as correlation between explanatory variables, that's going to exist in every equation where you have at least two explanatory variables. Our issue is going to be, when is there too much? We're going to have two main ways of checking for it: correlation coefficients and variance inflation factors. The variance inflation factor is going to be the more formal test. It's something I'll likely ask you to do in your final project. You'll kind of test to see if your own model has multicollinearity. Correlation coefficients is something you can do even before you run your first regression. So correlation coefficient is, we've used these in class before. It's the correlation coefficient that you learned about in stats. You probably learned about covariance and correlation coefficients. The correlation coefficient is the one that's measured between +1 and -1. Our threshold for two variables that are kind of too highly correlated, such that we suspect imperfect multicollinearity, is 0.8. If you have two variables who, without a regression, ignoring their impact on the outcome, just the two explanatory variables themselves have a correlation coefficient greater than 0.8 in absolute value, that is sort of an indication that there's likely imperfect multicollinearity going on. The more formal test is the variance inflation factor, or VIF test. The VIF test is something that you do after running the regression, and it's calculated separately for each independent variable in the model. I don't want you to sweat this equation. I want you to understand how to interpret the VIF test, and we're going to see it in Stata in just a second. The equation is here for those that are interested in it. The VIF is a measure of, if you treat each of your explanatory variables as if it were the outcome variable, the VIF is sort of a measure of how well do the other variables in your model, in this case x2, x3, all the way up to xk, how well do they predict x1? In other words, what is the r squared of this regression? If this r squared is really high, in other words, if x2, x3, x4, x5, and up to xk predict x1 really highly, and maybe that's just because x2 is super highly correlated with x1 and the rest don't matter, for whatever reason, or maybe it takes 4 or 5 variables, but if that r squared is really, really high, then the VIF is going to be really high, because the r squared will be close to 1, so this denominator is going to be really small, so the overall fraction is high. So a high VIF represents high imperfect multicollinearity. Our threshold for variance inflation factor is 5. If you see a VIF value greater than 5, then we're going to say that your model has imperfect multicollinearity. It's somewhat of an arbitrary threshold, but it's kind of being cautious. That is, by the time you get up to a variance inflation factor of 5, I think not only kind of in this class, but most economists would agree that the correlation is kind of beyond what would be considered normal in your data set. And what variance inflation factor stands for, is literally how much damage is this imperfect multicollinearity doing to your standard errors. So standard error is the square root of the variance. So if the variance is being inflated by 5 times or more, then that means your standard errors are kind of being inflated by the square root of that or more. So this is sort of saying if standard errors, the square root of 5 is like 2.25. So if our standard errors are at least 2.25 times larger than they should be, then we're going to consider that a problem. All right, what do you do about multicollinearity? And really, this is what do you do about imperfect multicollinearity? With perfect multicollinearity, you can't run a regression with perfectly multicollinear variables. Stata will automatically drop one for you because it literally can't distinguish the effects. For imperfect multicollinearity, the first thing to do is nothing. This is always a great thing to tell your parents when they ask you, hey, what did you learn in class today? Or, what did you write down on your test? And you just say, oh, I said do nothing. And I was right. Great. Boom. A+. So sometimes, especially in the case where the high correlation between explanatory variables sort of seems random, or theoretically it doesn't seem like the two things that are highly correlated, they don't seem to be measuring the same thing. That theory tells you that these are actually pretty different items, they're impacting the outcome in pretty different ways, and maybe just kind of a coincidence that they happen to be highly correlated in my data set. So one option is to do nothing. The second option, understandably, is to drop one of the imperfect multicollinear variables. That should then reduce the variance inflation factor and bring your standard errors back to normal. That's kind of what we saw in the student consumption versus disposable income and liquid assets example. The last thing is that you could always, if possible, increase your sample size. Sometimes, especially with small samples, when you only have 25, 30, 40 data points, things can be correlated kind of just by accident. In the very first lecture of class, I showed you that Nick Cage movies are correlated with drownings. Probably, so that study covered, I think, like a 15-year time span. Probably if we expanded that horizon beyond 15 years, the correlation would start to break apart. In other words, that sort of accidental multicollinearity usually can be solved by increasing the size of your sample. All right, so that's kind of it for the slides. I want to now show you a quick example of this in Stata, and then we'll come back to our table, fill it in, and we'll be done. So this is a data set that I think I used when I was teaching you about dummy variables in class. It is a data set for each observation is a James Bond movie. And I guess we can browse the data here. So we have the year the movie was released, the name of the movie, the actor who played James Bond. Our main outcome variable is going to be the gross, let's do the adjusted gross revenue of the movie. This is measured in thousands of dollars. So if this first movie, and all of these I believe have been adjusted for inflation, that's what the adjusted stands for. So 457,928, add 3 zeros after that. That sort of implies that the Dr. No, the first James Bond film, made $457 million in today's currency, or in 2012 dollars, I think. Then we have the budget of the movie. How much did the film studio spend producing it? And then we have, so the budget, so then we have gross revenue and budget. These are the same as adjusted gross revenue and adjusted budget, but in millions of dollars. So if this was 457,928, this is 457.928. So gross revenue is adjusted gross revenue divided by 1,000, and same for budget and adjusted budget. Then we have two variables that talk about the rating of the movie or the quality of the film. You have the Rotten Tomatoes score for the film, which is measured between 0 and 100, and you have the IMDb score for the film, which is measured between 0 and 10. So for those that aren't kind of movie buffs, these are two different websites, both of which allow fans and critics to go on and kind of rate movies on a numerical scale. So Rotten Tomatoes is kind of a percentage rating, it's out of 100, whereas IMDb uses a 10-point scale. What we're going to see in this example, though, is that even though they are separate rating systems, it tends to be that movies that are rated well on Rotten Tomatoes are rated well on IMDb, and vice versa, and so these two variables might potentially be imperfectly multicollinear. So let's start by doing a regression where our outcome variable is the adjusted gross of the movie, how much money the movie made in 2012 dollars. One explanatory variable is the budget of the movie in thousands of dollars. Our second explanatory variable is the budget of the movie in millions of dollars. Hint, hint, these two variables are perfectly multicollinear, so we'll see what happens in a second. And then we have two variables that both indicate sort of an indication of the movie's quality. How well did fans receive the movie? So, if we run this regression, first thing to notice is that budget gets dropped. Data can't calculate a standard error for it. Why? Because it's perfectly collinear with adjusted budget. It's impossible to hold the budget in millions of dollars constant while changing the budget in thousands of dollars. So that's perfect multicollinearity. Let's, just so that the screen looks a little better, let's just get budget out of there. And, all right, same thing. Now let's sort of look at the coefficients on Rotten Tomatoes and IMDb. Interestingly, neither of them are statistically significant. T-scores are both well below kind of any typical critical values. P-values are above 0.1. And so that's odd. We might think that the quality of a movie is an indication of how much money it's going to make, and that's not the case here. It's also odd that Rotten Tomatoes is very, very positive, indicating that a 1-point increase in your Rotten Tomatoes score increases the gross of a movie. So let me multiply 19,540 by 1,000, I think by $1.9 million. Whereas a 1-point increase in your IMDb rating is going to decrease the revenue of your movie by like $2.2 million. Or maybe 22? No, $22 million. Sorry, 19 million. 19 million for Rotten Tomatoes and 22 million for IMDb. And that's odd. And when I say that it is sometimes that imperfect multicollinearity makes it hard to understand or interpret a model, I would like for you to think to yourself, how would I describe to someone what it means to improve your Rotten Tomatoes rating of the movie by 1 unit while holding the IMDb rating constant? What does that kind of mean? What sort of real world situations does that describe? To understand that, you would maybe need to understand, okay, what is sort of the difference between Rotten Tomatoes raters versus IMDb voters? And so if the Rotten Tomatoes rating goes up by 1 but the IMDb stays the same, maybe IMDb or Rotten Tomatoes has maybe more critics on it, so maybe that's slightly a movie that critics like a little bit more than general fans, but both involve general fans. It just, understanding what it means to kind of hold one of these constant while changing the other one, it's just kind of murky. And that's often the case with imperfect multicollinearity. So let's go ahead and kind of do our 3 criteria for imperfect multicollinearity. The first one is we're just going to look at the correlation coefficients among all of these variables. How correlated are kind of the different things? And sure enough, our Rotten Tomatoes and our IMDb variables have a correlation coefficient of 0.95. This is clear evidence of variables that are likely imperfectly multicollinear. The next thing we can do, I'll put the regression back up here, is you run the variance inflation factor command. Recall that for heteroscedasticity, the command was estat. That means generate a statistical estimate a statistic. For heteroscedasticity, we did the het test, right-hand side. We could do that right now. So no evidence of heteroscedasticity in this model. For the VIF test, we're just going to type estat VIF. Pretty intuitive, no options, no comma. And you have to run this after you run the regression. And what we have here is that both the Rotten Tomatoes and the IMDb have VIFs well above 5. This is indicating that sort of including both of these in our model is inflating the standard errors maybe by like 3 or 4 times, because the variance is going up by 12 times, what you would normally expect if one of them weren't in the model. Okay? Whereas the budget has a very low variance inflation factor because the adjusted budget is probably not all that correlated with ratings. It's not too terribly correlated with the other explanatory variables in the model. So the 3 things, going back to our slides, kind of the 3 remedies for multicollinearity. One would be to do nothing. In this case, the coefficients on Rotten Tomatoes and IMDb were kind of so weird, with one being super positive and one super negative, that doing nothing doesn't strike me as correct in this case. It's pretty clear that they're both measuring the same thing, so we probably should do something about it. I don't think this is a case where if we just got more data, the correlation would go away. Drop a redundant variable. This is what we're going to try. We're going to look at the model without each of these 2 variables and see how things change. Or increase the size of the sample. Not an option in this case. I guess I could go, I've been lazy, I haven't downloaded the data for Spectre, the movie since Skyfall. I could increase the sample size by 1, but we can't make a real meaningful change to the sample size here. So here, let me do tomatoes. So here's the regression without the IMDb rating. Notice that the Rotten Tomato score is now 17,262, so a 1 point increase in your Rotten Tomato score relays or corresponds to like a $17 million increase in the movie's revenue. That seems sensible. The coefficient is actually pretty similar to what it was before, 19 million compared to 17 million, kind of in the same ballpark for sure. It's within the 95% confidence interval, but now it's statistically significant, which at least theoretically kind of makes sense. You would think that movies that are better reviewed should make more money, kind of all else being equal. Now let me look at the impact of the IMDb rating without the Rotten Tomatoes rating. And here we go. Another positive and statistically significant coefficient. That is, when we're not looking at the impact of the IMDb movie rating holding Rotten Tomatoes constant, when we're just looking at what's the impact of your IMDb rating on the take of the film, just holding the budget constant, we get virtually the same effect as with Rotten Tomatoes. This effect is about 10 times larger than Rotten Tomatoes, but that's because the IMDb rating system is on a scale 10 points or 10 times smaller. It's 0 to 10, whereas Rotten Tomatoes is 0 to 100. So going from a 6 to a 7 in IMDb rating is equivalent to going from a 60 to a 70 in Rotten Tomatoes. So this model is likely a lot easier to interpret when we only include kind of one measure of rating rather than both. It's both easier to interpret and we're avoiding the variance inflation problem. And so we kind of get a statistically significant result where we sort of really think there should be one. I guess as a last kind of check is you can always also just plot the data to kind of look at them. This is going to tell you something pretty similar to the correlation coefficient, but sure enough, these data look to be pretty highly correlated across the movies. There aren't higher IMDb rating almost always means higher Rotten Tomatoes rating. All right, so let's kind of wrap this thing up. We have our method for detecting perfect multicollinearity is theory. Our method for detecting imperfect multicollinearity is either a correlation coefficient greater than 0.8 or a VIF test above 5. I guess you could also use a scatter plot. And then how do we deal with multicollinearity? For perfect multicollinearity, you kind of only have one option, and that is to remove the variable. Stata will actually auto-drop two variables that are perfectly multicollinear. I'm also going to include increase the sample size as a potential correction, because sometimes it's going to be the case, let's say that you're studying businesses and we're using the example where you're considering a business's total revenue versus their tax revenue. Well, if all of your businesses are in the city of LA that has the same tax rate, then those two things will be perfectly multicollinear. Perfectly multicollinear. However, if you increase your sample maybe to businesses all around California or businesses in large metropolitan areas, increasing your sample might kind of break up the mechanical relationship between those two things. So sometimes increasing your sample size is a way to get rid of perfect multicollinearity. And then for imperfect multicollinearity, our three options are do nothing. This is the case if the variables in question kind of theory tells you that they're measuring pretty different inputs. They just kind of happen to be correlated. Your second option is to remove one or more of the variables. Removing one of the variables with a VIF greater than 5 should then reduce the other variable's VIF that remains in the model. And your last option is to increase your sample size. That's going to not be a very feasible option for most of us when it comes to final projects, because really, once you've collected your data set, it would be an unfair burden for me to ask of you to go out and just find more data just to fix multicollinearity. So instead, in terms of final projects, most of you will be taking either options 1 or 2, either doing nothing if theory tells you that's okay, or removing one or more of the variables in question. All right, guys. That's it for multicollinearity. The VIF test for this, the HET test for heteroscedasticity, both things I'm going to be asking you to do on your final projects, things that we're going to be practicing in our labs this week and maybe also next week. We really only have one lecture of mine left, serial correlation. Look forward to that because what you get during that lecture is serial-based puns. So if you have any of those, start thinking of them because I will be asking for them when we do our worksheet in lab around serial correlation. For now, though, stay safe, stay healthy. I will see hopefully most of you guys in class very soon.